Welcome to the Deep Dive. We're diving into the world of electromagnetism today.
Ooh, sounds electrifying.
It is, actually. We're tackling a college-level physics lecture on this invisible force that powers so much of our world.
I bet most people don't realize how much they rely on electromagnetism every single day.
Exactly. So we'll break down concepts like induced EMF and AC circuits.
Make sure your brain doesn't short circuit.
Haha, exactly. Let's start with something called magnetic field flux. Our source material describes it as, well, imagine magnetic field lines passing through a loop of wire.
It's like if you picture a hoop in a flowing river, the amount of water passing through is kind of like the magnetic flux.
So the angle of that hoop, or the wire loop in this case, matters.
Big time. If the loop's perpendicular to those magnetic field lines, like the hoop's facing the current head-on, you get the most flow.
Makes sense. So is that where the whole generating electricity thing comes in?
You got it. This changing magnetic flux is the key ingredient.
And here comes Lenz Faraday's law. This one always felt kind of magical to me.
Right. It's pure physics, but feels like magic. It basically says, change the magnetic flux through a wire loop, and bam, you get voltage.
So like just having a magnet near a wire isn't enough. It's the movement that makes the electricity.
Exactly. And then there's Lenz's law on top of that, which adds a little twist.
Okay, what's the twist?
The induced current. It creates its own magnetic field that pushes back against the change in flux.
Whoa, so it's like nature's trying to keep things balanced.
It's a great way to put it. Like the system wants to resist that change you're forcing on it.
So we've got these fields, changing flux, voltage. But how do we get to the electricity we actually use?
Generators. They're the rock stars of our electrical grid.
I'm picturing those giant wind turbines.
Perfect example. Those spinning blades are rotating coils of wire inside a magnetic field.
So they're constantly changing the magnetic flux.
And that's inducing a voltage, hence electricity.
So basically, giant magnets spinning around, creating power from thin air.
Not quite thin air. They're harnessing the wind's energy, but yeah, the principle's there.
That's mind-blowing. Okay, so we've made electricity. How does it get to our houses?
AC circuits, right?
You got it. Alternating current is the most common type, and it's all about change.
How so?
The voltage and current, they're constantly switching directions, following this wave-like pattern.
So instead of a steady flow, it's more like the electrons are doing a dance.
Uh-huh. Love that analogy.
Oh.
And the speed of the dance depends on the frequency, how often it changes direction.
Higher frequency, faster dancing electrons.
Precisely. Now, you can't forget about the other players in these circuits, resistors, capacitors, and inductors.
Right, they control the flow, don't they?
They're like the choreographers of this electron dance, each with their own style.
Okay, break it down for me.
Resistors are the simplest, they just limit how much current can pass through.
Like a bottleneck?
Exactly. And some of that electrical energy gets turned into heat by the resistor.
Ah, that's how old light bulbs worked. What about capacitors? They store energy, right?
Think of them like tiny batteries that can quickly charge and release energy. So they respond to the changing voltage, kind of like anticipating the next step in the dance.
You got it. Then you've got inductors. They're a bit more rebellious.
Rebellious how?
They resist any sudden changes to the current, prefer a smooth, gradual flow.
The inductors, like the grounding force in this wild electron party.
A good way to think about it, they help protect delicate components by keeping things stable.
So we've got this whole intricate dance going on inside our electronics.
And it gets even more amazing when you put resistors, capacitors, and inductors all together in a circuit.
That's where the real magic happens, I bet.
It's like a full-blown electrical symphony. Each component affects the others, creating these really cool phenomena.
Okay, now I have to hear more about this electrical symphony. So you were saying how things get really interesting when you put resistors, capacitors, and inductors all together in a circuit.
It's like, you've got this constant back and forth of the AC current.
Like our electric slide analogy.
Exactly. But each of these components, they kind of react to it differently.
Right. The resistor wants to keep things steady, the capacitor stores and releases, and the inductor resists any sudden changes.
It's almost like they're having these little mini battles, but it all works out in the end.
So how does that actually play out in the circuit itself, like with the voltage and current?
Well, imagine you've got this sine wave, right, representing the AC current.
Okay, got it.
Now, the voltage across each of those components, it won't necessarily line up perfectly with that wave.
So some parts of the circuit are kind of out of sync with the others.
Yeah, it's like a dance where everyone's got their own little variations on the steps.
Okay, so walk me through each dancer then.
So the resistor, that's the simplest one. Its voltage just rises and falls in sync with the current. No drama there.
So the resistor's like the one who knows the routine perfectly.
Now, the capacitor, that's a bit different. Its voltage lags behind the current a little bit.
Like it's taking its time to catch up with the beat.
Exactly. It takes a moment for it to charge and discharge, you see.
Makes sense. And then there's the inductor, the rebel.
The inductor. Its voltage actually leads the current. Like it's anticipating the next move.
So it's like the one showing off some fancy footwork.
You could say that. Remember how it resists changes? So when the current's about to rise, it kind of pushes back first.
Wow, so this is way more than just electrons moving back and forth.
Oh, yeah. There's this whole interplay happening, all driven by the changing current.
So this is where the whole resonance thing comes in.
You got it. By adjusting those component values, we can actually tune the circuit to resonate at a specific frequency.
Okay, remind me what resonance means again.
Think about like a tuning fork.
Oh yeah, how we can make another object vibrate at the same frequency.
It's the same idea in an electrical circuit. When it resonates, it's like it's amplifying that specific frequency, blocking out others.
So is that how radios work?
You guessed it. By tweaking the circuit, you change which frequency it resonates with, and that's how you tune into different stations.
That's amazing. So we're talking about the same principles here, whether it's sound waves or electrical circuits.
And it goes even further than that. Resonance is also used in, say, wireless charging.
Wait, so the same thing that lets me listen to the radio is how my phone charges wirelessly?
Absolutely. Remember how a changing magnetic field can induce a current in a wire?
Yeah, like with generators?
Well, a wireless charging pad, it creates this changing magnetic field that can resonate with a receiver in your phone.
So it's sending out these magnetic signals, and my phone's tuned to pick them up.
Exactly. That receiver's part of a circuit designed to resonate at just the right frequency.
So it's like they're speaking the same electrical language, allowing energy to transfer without any wires.
You've got it. And it all comes back to these fundamental ideas we've been talking about.
This is incredible. It's amazing how these simple concepts can lead to such complex technology.
And we haven't even scratched the surface of all the applications of electromagnetism out there.
There's a whole universe of things we could talk about.
You're telling me. But for now, why don't we shift gears and dive into the world of wireless communication? It's where things really start to feel like magic, even though it's still all based on these same principles.
Okay, I'm ready for some more mind-blowing concepts. Okay, wireless communication, let's get into it. It does sound kind of magical.
Right, like sending information through thin air, but it's those electromagnetic waves again.
So we're not talking about electrons and wires anymore. It's these waves carrying the information.
Exactly. And they can carry anything, really. Music, messages, even video calls, all thanks to electromagnetism.
But how do you even attach information to a wave? It seems so abstract.
It's actually pretty clever. We call it modulation. It's basically modifying the wave itself, things like its amplitude or frequency, to represent the information.
So it's like changing the wave to carry a code.
You got it. And then the receiver knows how to read that code and get the information back out.
Okay, I think I'm following, but how do these waves actually travel? Don't they need wires to guide them?
That's where antennas come in. They act like, I guess you could say, transmitters and receivers for these waves.
So my phone has an antenna to send the waves out, and my headphones have one to pick them up.
Exactly. The transmitting antenna takes the electrical signal, converts it into a wave, and sends it out.
And the receiving antenna does the opposite, turning the wave back into an electrical signal.
You got it. It's pretty neat how it all works together.
But how do the waves know where to go? Like, wouldn't they just get lost in the air?
That's where frequency comes in. Remember how we talked about AC current having a frequency, like how fast it oscillates?
Yeah, like our electric slide analogy.
Well, electromagnetic waves have frequencies too. And by using different frequencies for different types of communication, we make sure they don't interfere with each other.
So it's like each type of signal gets its own dedicated channel.
That's a good way to think about it. Bluetooth, Wi-Fi, cell phones, they all operate on their own specific frequency bands.
So it's like an organized system where everyone's transmitting, but nobody's stepping on each other's toes.
Exactly. It's pretty amazing how it all works together seamlessly thanks to our understanding of electromagnetism.
This has been an incredible deep dive. From basic magnets to wireless communication, it's all connected.
It just goes to show how powerful these fundamental forces of nature are.
And who knows what we'll be able to do with electromagnetism in the future.
The possibilities are pretty much endless.
Well, I think we've given everyone a lot to think about today, from the electricity in our homes to the invisible waves connecting us.
Hopefully we've sparked some curiosity about the unseen forces all around us.
Definitely. If you want to keep learning more, there's a whole world of knowledge out there waiting to be explored. Until next time, Keep those brains buzzing, deep divers.